Hi, this screencast is on sections 1.5 and 1.6. So before we get started, a couple things to think about with the AP classroom assignments. I know they're very challenging. It starts with just knowing the content, which is challenging enough, but then the problems require you to problem solve and think. So make sure you understand all the content, but also make sure that you put in thought and effort into those AP classroom questions, because the only way to get better at problem solving is to go through and solve problems. So make sure you're doing that, and please ask questions as you go. So the first section for today is 1.5 on atomic structure and electron configuration. So the learning objective is to represent the electron configuration of an element or ions of an element using the Aufbau principle. So some essential knowledge, and there's quite a few things that you need to know in this section. The first one is just basic atomic structure. And all you really need to know here is that there's a nucleus which contains protons and neutrons, which overall has a positive charge, and then that's surrounded by a cloud of electrons. So and that's really, there's a lot to atomic structure, but in AP chemistry, that's essentially all that we need to know. All right, and then we get to Coulomb's law. So Coulomb's law, and we've heard this a few times in a few different sections. Coulomb's law is proportional to charge over distance. And in this section, it's referring to ionization energy. So really the two variables here, for the charge, it's going to be the number of protons that are in the nucleus, because the charge of electrons, they're all the same, they're all consistent. But the nucleus can have more or fewer protons, which will affect the charge. And the distance is going to be the distance from the electron in question to the nucleus. So electrons that are farther away from the nucleus will have a greater distance, therefore a weaker Coulombic force and a lower ionization energy. So it takes less energy to remove that electron from the atom. To continue on with 1.5, you want to know about core electrons and valence electrons. So core electrons are essentially just the inner electrons. They're not involved in chemical reactions. Valence electrons are the electrons that are farthest away from the nucleus. They're the electrons that get lost, shared in chemical reactions. So you can get the number of valence electrons just simply by placement on the periodic table. So the first column will have 1, second column will have 2, and then over here we go 3, 4, 5, 6, 7, and 8, except for helium, which only has 2. The transition metals and the intertransition metals down here, they do some different things with their valence electrons, so we don't really have a set rule on that. And then you also want to know about energy levels and sublevels and how we can get that from the periodic table. So the energy level is essentially just the row on the periodic table. A sublevel, that's referring to S, P, D, or F. So the different blocks on the periodic table. So these first two columns right here, that is your S block, and helium is part of that S block also. The last 6 columns on your periodic table, that's your P block. This middle section right here, the transition metals, that's the D block, and down here, that's your F block. So those are the different sublevels on the periodic table. We don't need to know anything about quantum numbers, so if you ever see that in your review book, that's not something that you need to know. But we do need to know about electron configurations of atoms or ions. So just a couple practice there. So let's look at manganese, Mn. All right, so you want to know the shortcut methods or noble gas notation. So it starts with the nearest noble gas behind the element. So in the case of manganese, it's going to be argon. And we just put argon in brackets. And that just represents all these sublevels and energy levels filled up to argon. And noble gases are a good starting point because they have full energy levels. All right, so then we continue on the next row. This is in the fourth period, so it's going to be 4s2. And the number in front of the letter, that represents the energy level. The letter represents our sublevel. And the superscript, that represents the number of electrons in that sublevel. Then continue on until we get to manganese. So the next section is going to be 3D. If you remember, the energy level of the D block is 1 less than the row that it's in. So although this is in the fourth period, the energy level for this D sublevel is 3. And then a D sublevel can hold 10 electrons, but manganese is the 5th one in, so it's going to end 3D5. All right, so that's an example for manganese. Now you also want to do electron configurations for ions. So let's say let's take the fluoride ion, for example, which has a -1 charge. So fluoride is going to end up being just like neon. So start from the beginning, we would put helium in brackets. That's the nearest noble gas behind it. And then you start in the second period, so it's going to be 2s2, and then 2p. And fluorine is the 5th element in that P sublevel, so if it was the fluorine atom, it'd be 2p5. But since we have the negative ion, it's going to add 1 more electron, so it ends up 2p6. So it ends up, you could say that the fluoride ion and the neon atom are isoelectronic. Isoelectronic just means they have the same number of electrons. So the representative elements, which is your S block and your P block, when they turn into ions, they become isoelectronic with the noble gases. Now the transition metals, it's a little bit different. Say we take, instead of the manganese atom, now let's say it's manganese +2. So in the process of becoming a +2 ion, it lost 2 electrons. Now the question is, which 2 electrons does it lose? Does this turn down to 3? What really happens is that we get rid of the S electrons. So that's something that you want to remember. When transition metals turn into positive ions, the first electrons that they lose are S electrons. Okay. Next is photoelectron spectroscopy. So the learning objective here is explain the relationship between the photoelectron spectrum of an atom or an ion and A, the electron configuration of the species, and B, the interactions between the electrons in the nucleus. So this is what photoelectron spectroscopy data looks like. It has these different peaks right here. We'll look at this in a bigger picture on the next slide. But the essential knowledge is, should be able to tell 2 things from the data. You don't have to know how the spectroscopy works. You just have to be able to analyze the data. So the first thing we can see is, 1, the position of each peak is related to the energy required to remove an electron. And 2, the height of each peak is proportional to the number of electrons in a sublevel. So we'll talk about this on this slide right here. Okay, so when you look at the data, on the y-axis you get the number of electrons. On the x-axis you're going to see energy. Now in this case it says megajoules per mole. This could also just be labeled as energy or maybe binding energy. But what you really want to focus on is, where's your highest energy peak? So you want to make sure that it's going from 1,000 here to 0.1. So the highest energy peak is going to be the farthest left. The first peak the peak with the most energy is always going to be your 1s peak. So that is what you base everything else off of. So the height of that peak is, it says 2 right here for the electrons. Even if you didn't have that, you should know that the 1s sublevel can hold 2 electrons. So the height of this peak right here is going to be relative to all these. It's going to have 2 electrons. So now you can continue on and just understanding electron configurations. The next peak out would be 2s, and it's the same height right here, so it's going to be 2s2. The next peak, if you go by the order of sublevels for electron configurations, is going to be 2p, and this is 3 times higher than these other peaks, so it's going to be 2p6. And the next peak out is going to be 3s, and that's the same height as these first 2 peaks, so that's also going to contain 2 electrons. And then it tells you it's magnesium right here, but what you could do, you could just look at 3s2, and you find that on the periodic table, and it's magnesium. All right, now a couple things with this. So first of all, if you could do a calculation for ionization energy, in that you just have to look at the amount of energy here. It's in megajoules per mole. You could do conversions with that to get joules per atom or joules per ion or joules per electron to figure out ionization energy with a calculation right there. All right. Another thing you think about that you might have to be able to compare different elements. If you say this is magnesium, if you had, say, aluminum, what the peaks would look like in aluminum is it would be shifted a little bit left. So the aluminum peak would be like right there, something like that, because aluminum has 1 more proton in the nucleus. So the binding energy will be a little bit greater. So all the aluminum peaks would just be shifted just a little bit left. They'd be the same height, but they'd be a little bit left of what we see for magnesium. Other than that, that's about all the information that you have to be able to determine with photoelectron spectroscopy. You have an AP classroom assignment. Send me emails if you have any questions on that. Have a good day.